Thank you. I'd just like to make a comment on the septic tanks. Miami-Dade County has thousands of septic tanks in the city on small lots from 7 to 10,000 square foot lots. And that's a big contributor to their algae problem around the city of Miami. So it's not just a rural problem, it's also a city problem. Okay. What I'd like to talk to you today about is using desalination to treat brackish and seawater for an alternative water supply. I'm, again, Matt Trzcinski with CDM Smith. I'm a desalination discipline lead with the company. I work out of the Tampa office. I lived in Texas for a while. I worked on the K. Bailey Hutchinson facility, worked overseas, both industrial and municipal projects, and this is a passion of mine. So today I'm going to talk about, why to desalinate, some desalination technologies, the reverse osmosis process, which is really the most common desalination technology in use today, implementing reverse osmosis technology in a project, and I'll run through a couple example projects. I have a couple slides on two projects, but hearing what they've done in the wastewater and discussion on PFAS, a lot of reverse osmosis can also be used for this type of treatment also. So why desalinate? Well, here's some facts. In Texas, they're expecting a 50% population boom by the year 2060. And desalination is an accepted technology or process to treat brackish and seawater to produce potable water. And in addition, TCEQ has streamlined this whole desalination approval process. And this is both for seawater and for brackish water desalination. So as you can see from this slide here, the blue represents areas where brackish water exists in the groundwater. And the darker the blue is, the deeper you have to go. So the lighter blue areas are shallower brackish waters. And then in addition, you look at the coastline across the US. There's about 6,000 miles of coastline. Texas probably has close to approximately 370 of those. Why desalinate? Now, there's 2.7 billion acre feet of brackish groundwater in Texas, which is fairly easily acceptable, as you'll see in a couple of slides coming up. The brackish water is available in all regional planning groups. Brackish water is available in most major and minor aquifers in the state of Texas. And also from this slide here, you could see the brackish, you could see first of all, the wells on the left-hand side show the amount of wells across the state, with the blue being the freshwater wells, and the larger graphic on the right is showing the brackish water wells, both from water from less than 3,000 TDS and then from 3,000 to 10,000 TDS. And as you can see down here in South Texas, there's quite a few wells. They said it was going to get stuck. All right. So just from a very high level, I'd like to talk about the brackish saline and seawater salinity. So typically brackish water, people look at it from like 1,000 to 10,000 milligrams per liter, saline from 10 to 30,000, and seawater's typically above 30,000. So, but from a big picture standpoint, brackish water, people talk about 15, 20,000 TDS. In Tampa Bay Water has a desalination plant. They pull water out of the Tampa Bay, and that water is about 27,000. It varies a little bit due to the tidal flow, but that's considered seawater desalination, which again is well below 30,000. So this is just a general group of salinities here bracketed. So here's some common technologies used. Thermal is really big, especially in the Middle East. And then there's membrane technologies. There's electrodialysis reversal and the reverse osmosis. In the Middle East, even now, even with the low cost of energy there, they are now implementing many large seawater desalination projects using membrane technologies. So now I'll talk about the reverse osmosis process. So why reverse osmosis? In Texas, that's the most common technology used for desalination. Not only Texas, I would say worldwide, both from a municipal perspective and also from an industrial perspective. It's a highly adaptive process that will handle various salinities of brackish water and seawater. So it's just at what temperature or what pressure you're operating at and what recovery you're operating at. And here it breaks it down typically for something up to about 3,000 TDS, you're operating about 300 PSI at the max. And for saline waters, you go from 350 to about 600 PSI. And then for seawater, typically 600 to 1,200 PSI. Temperature comes into play on that, as well as recovery and it's temperature and recovery impacts the pressure that you're operating at. And then here I have a graphic on what reverse osmosis removes. And as you'll see, conventional filtration is up there on the right-hand side, where reverse osmosis is down to the molecular weight removal of compounds and ions. It's very good in addressing a lot of these emerging contaminants, especially PFAS. In the state of Florida, the membrane technologies, reverse osmosis. When I talk about reverse osmosis, I also include nanofiltration. So nanofiltration, brackish water, seawater are essentially a reverse osmosis process. But they use that in the state of Florida because there's a lot of organics in the groundwater as well as hardness. And then now they're addressing the emerging contaminants also with it. So again, addressing the different types of application, nanofiltration, softening, color removal from organics, emerging contaminants, PFAS removal, selective ion rejection membranes. In the oil and gas industry, they have a membrane that will reject sulfate extremely well. So they take seawater, about 35,000 parts per million, and they'll end up with their permeate, which is still about 28,000 ppm of TDS, but it removes virtually all the sulfate, all the calcium, all the magnesium. It's used in brackish water desalination, both for potable applications and a lot of industrial applications. You go to the electronics industry, they use that commonly to produce it's the upfront treatment process to produce high purity water. And again, with seawater desalination, it's the most common technology used around the world. Okay, implementing a reverse osmosis project. I'm going to go through a couple items here, and this is just really high level stuff, but big things to consider that a lot of people really don't look at is really identify and begin the permitting process very early for brine management, because that's the biggest issue that you're going to face with when you implement the project. And select the contracting methodology to help you deliver the project with the level of effort that you want to contribute to it. Do you want a specification and you're just worried about the water quality, or do you really want to be involved and talk about, the type of equipment that you want and so on? And then from the concept select phase basis of design, understand energy use on the project, because desalination is the highest from a water treatment perspective in the US, uses the most amount of energy. So you have to understand that use, the efficiencies in the treatment process, as well as the power availability in the area. And also in considering the design, the novelty and complexity of the project. Most of the technologies and the unit processes in desalination are new technologies to operators, so you got to get them involved early in the project. Brine management is again one of the key issues, especially seawater desalination, where you have a discharge to the ocean. So they want to look at toxicity testing. How are you going to manage it? Diffusing it, dispersion, and a lot of times it's a lot of places will dilute it with the wastewater that's being discharged to the ocean also. And you want to consider, on the right there, I got filter backwash and all the residuals that are involved in the treatment process. Because it's not just desalination. You'll have a lot of solids that you have to remove. They may have a DAF process. You may have ultrafiltration. You may have a conventional filtration prior to the RO process. And you have to deal with all those solids. From a brackish water perspective, there's a couple things that you could do. There's, again, surface water. It could be to creeks. It could be diluted again with creeks. And then there's underground injection control. So it's used here in Texas. It's used commonly in the state of Florida also. And if you're going to do the underground injection control, you want to be able to do the testing to make sure the compatibility with the fluid you're injecting is compatible, not only with the fluid that you're injecting it into the well, but also the well formation itself. Looking at contracting methodologies, I'm sure everybody here is familiar with at least some of these, but there's a typical design bid build and all the various alternative project delivery methodologies, and some go as far as just hiring an operator to operate the plant for you and then turn it over. So there's a wide variation in that, and that all comes into play with how much time you as an owner want to spend dictating what that project will be. Is it just going to be prescriptive, where you're looking just at getting so much water or a certain water quality, or are you really going to look at it in the future, you operating it, your operators there, what they're going to do with it? And then implementing lessons learned. Always involve all stakeholders. That's the biggest thing I've learned over my career, is get everybody involved. And that's both internally and externally, whether it's the community, what have they learned, what have they learned in the past on how you're dealing with projects. Bad news always comes out. It's deal with it up front, deal with all the concerns that people have. Internally, whether it's the contractor, the vendors, the engineers, the owners, take your lessons learned, bring them to the table, and implement them in the project. And as I said, understand energy use, right? So how you design the system. If you want to use less water, that means you're going to have a higher recovery. A higher recovery means you're going to use more energy. You're going to look at how are you going to operate it in terms of flux. Flux is the amount of water going through the membrane over a given period of time. So the higher the flux would be the lower cost, the less you spend for membranes, but it'll have energy impact to it. And then there's various types of energy recovery devices. They still use the Pelton wheel, which is very rare nowadays, but they do have that. They have pressure exchangers, and then they have these turbos that they typically use on the brackish water plants. And then from the novelty and complexity, again, as I stated, a lot of this will be new to operations, so you get them involved early in the project. You bring them on while the project's being constructed. Start training early, recruitment and training. And then I'll go through some example projects here. So this one is a Monterey Peninsula project, which is a private water company. And this started years ago, probably 15 years ago in the state of California. And then this project was really brought about that they wanted to get off the supply of surface water from the Carmel River. And this was more from an environmental standpoint. And the project, it's a program. It's involves a private company in California. It's a $320 million program, though the plant is not $320 million. I believe it's a little less than $100 $400 million. The plant is designed for 9.6 in 2 phases, would be 4.8, and then expand it further. And then what they're using is a slant well technology where they're not having an open intake where you worry about impingement and entrainment of sea creatures. So they're taking it below the ocean floor, basically like a well, and these are slant wells that they use. And this is the first such technology used in Northern California. And then a local project here is the K. Bailey Hutchinson facility, which I was personally involved in that facility. So this facility, it really was brought on board because their freshwater wells were being depleted, and there were issues with taking water from the Rio Grande at different times of the year. So they went and they developed this project. It was a 27.5 million gallon a day plant, but the membranes itself were producing 15 million gallons. So they were blending about 12.5 million gallons. And as I stated earlier in the slide, I talked about how the membranes are very versatile for changing water qualities. Over the years, the water quality, the salinity has just gotten worse. So there were the membrane systems were able to still treat it. They had to do some slight modifications where they put a booster pump in. It was originally designed where it didn't have that in between the stages to allow for this treatment of higher salinity water. The plant's being currently expanded to add a 6th train, so they'll be able to produce 18 MGD of permeate and over 30 MGD of blended water. It won several awards, and it involved all kinds of studies. There were pilot studies done that took over a year. We looked at recoveries, operating the plant up to 92% recovery, looked at using various anti-scalants. We looked at different types of designs, and you could see from our old plant, this is a very unique design, and this was done just to handle the airflow through the system, where I learned on other projects that you would get a lot of fouling of the membranes just due to the oxidation of iron and manganese. So this solved a lot of the problems there. We did a lot of modeling, and a lot of this information was required. And this, again, keep in mind, was coming up on 20 years ago. And TCEQ required all this information to permit the plant. And it involved building a separate facility there. I don't know, probably several of you have been out there at any of the conferences where they're pretty proud of what they do. It's a water center there where they talk about water scarcity and what they've done over the years to reduce water consumption in the city. And then there's some other projects that I don't have here. This is my last slide. But what I wanted to address was really how RO membranes are being used to treat emerging contaminants, in particular the PFAS. So at CDM, we have done quite a bit of work over the years. We have a research center where they've I think it's like $2 million over the past 3 or 4 years invested just in PFAS research. So, we've looked at it. It's very, RO is popular in Florida for the treatment of PFAS, just due to the fact that they have organics, which organics load up both ion exchange and the carbon. So it makes it cost prohibitive, where they could deal with it with the RO membranes. Questions?
All right, so we'll open up for the audience here in a second. I do have a few questions. Now, we will go from softball questions to the hard ones, because I think there's going to be some tougher ones, and we will allow questions from the audience as long as everyone is respectful, because I know this is a hot topic issue. First one, do you have any concerns, as you spoke a little bit about it, about the PFABs and desalination?
Any concerns?
Yeah, any
Well,
concerns, benefits?
my biggest concern would be, and I think there was a mention of it before, is you're still going to have a residual waste stream. So how do you deal with that residual waste stream? So with the GAC and with an ion exchange, they take that and that's disposed of. I think a lot of times that's incinerated eventually. But with the reverse osmosis, you have a brine discharge stream. So currently, in Florida, what they're doing a lot of is deep well injection, which it's permitted. But I know one of the compounds that fall under this PFAS umbrella is considered hazardous waste, and eventually I see it coming around where that's going to be regulated also. So you'll probably have to address the brine issue of removing PFAS from the brine. So that's a concern.
All right, thank you. And I really like this next question. I'm not sure who asked this one. This is a really good one. Given the advanced treatments needed, has there been any projects that use commingling of like treated wastewater and seawater?
Treated waste. Let me think. Well, in terms of treating it, is that the question?
I guess like blending the seawater with the treated water to maybe lower your desalination levels and those types of things. Has that ever been looked at?
I haven't heard of it, but that sounds like a pretty good idea. Since they're
right, that's the way I read it.
Yeah, no, I mean, since they're doing indirect and direct potable reuse, that sounds like a very good approach, though I'm not aware of any projects that currently involve that.
Do you know how much the El Paso project cost and what it cost to yearly operate it?
I don't know the yearly operation cost as of now, but when that project was constructed, I believe it was $30 million. I would assume today that project would probably be $150 million.
All right, I will do this for the audience because it's been asked more than once. In your opinion, would you prefer to build a plant inside of a closed bay or an open ocean?
Personally, probably open ocean would be easier, just from being able to run pipelines in and out of the ocean. But there's a lot of cost involved in piping in the water. So there's a trade-off. So from a treatment perspective, it's easier to treat water that's offshore than from inside a bay. That you have to deal with a lot of the pollutants in the bay. So that's a big concern. But then you have to pipe. So there's the environmental issue of running pipelines from the coast to wherever you want to bring the water. So it's a trade-off. So from a treatment perspective, it's easier to treat the water. From a cost perspective, I believe it's more cost-effective to have it inland.
Thank you. Are there any questions here from the audience?
How much did the big Nueces plant cost, and where did the majority of that water go to? Was it to the residential use?
Yes, it was. Yes, it was the residential use. It was, and as I stated, it was around 30 million, 32 million, if my memory serves me correctly. Pardon me? $32 million. Yeah. So, and again, that was 15, 18 years ago.
Any other questions from the audience? I believe you said that was mainly used for residential.
Yes, it's a residential. The plant is built on the Fort Bliss, so it's actually built on the military base. It uses deep well injection, so it has a class 1 injection well that was designed. I believe it's like 15, 20 miles that goes out into the base, and it was designed. The pipelines were designed for it to have tanks run over it and everything else. But it is a deep well injection, and to this day, the plant is performing extremely well. I'm sure they'd be more than happy to show it off for those that are interested in brackish water desalination. And feel free to contact me also.
Any other questions? Or thank you, Matthew.
All right, thank you.